So we'll go ahead and get started. Keep hearing this question. The test is Tuesday. So be ready for that. I did post a study guide, so that information is up there. Most of the test is ultimately looking at balancing reactions, or what type of reactions we've got. So almost all of it is chapter 7. And I would argue even the stuff we're going to talk about today is still manipulating balanced reactions. Okay, so it's still an overlap of chapter 7. I will hold office hours tomorrow from about 9 to 11. I know the tutoring center opens at 10, but Laura Tracy, who runs it, gets in a little bit earlier, and so she's almost always here by 9 and has it unlocked. So I will head there as soon as I get in. So it should be about 9. 9 to 11. 9 to 11. Okay. Yes?
I was looking at the syllabus today, and it said that the exam and the final exam all will be completely multiple choice, but that hasn't been the case.
Oh, interesting question, or interesting point. So typically the reason I do extra things outside of multiple choice is that if you look at the average on points from multiple choice versus points from short answer, the average points on multiple choice is usually about 50%, and the average for short answer is about 70%. I don't know why I decided to switch to short answer for this one. I know in other classes I've always said multiple choice, and then people asked for short answer. I don't think anybody asked for short answer this semester. It is consistently higher, so that might have been what it was, is I just decided to do it.
So there's going to be more short answer on this exam?
No, if anything, there'd be less, because we're getting closer and closer to the final, and the final is strictly multiple choice. Yeah, the final is absolutely 100% multiple choice. There is no short answer.
Is it over everything?
And it covers everything, completely 100% cumulative.
How many questions are there?
On the final, 65 questions, I think. Your exam, you should expect somewhere in the 40 ballpark, because you're having a little bit less time. The final exam is an hour and 50 minutes long, so there's an extra 45 minutes. The practice has a little bit more, I noticed. I don't know why that is. There is a practice final. As far as I could tell, yes. I didn't make the final or the practice exam. Those were all made by the department, and they went through. It's on Canvas somewhere. Anybody remember where on Canvas?
Where do you go?
Files. Oh, it might be in announcements too. If you check your announcements, you might see the link. It may have been sent out as an announcement, and if you've got your settings set properly or set in that way, the announcements will come to you as an email. Yeah. So it should be under files. If you send me an email, I'll go through and try and redirect you towards it, but it is posted there. Okay. Other and general questions?
So files under this class?
Yes, files. Well, it wouldn't be files for organic chemistry.
Well, no.
If you get it up there, let me know, and I'll come back around and point it out.
It's under files again.
There you go. Finals, exam keys. Oh, which means there's keys for all the other exams too. I did post those, didn't I? For 1 and 2. Yeah. Okay, in any case, what we're dealing with today. Ultimately, all it is dimensional analysis. Chapter 8, we bring up one new conversion factor. That conversion factor happens to be a mole. So what is a mole? And that's all chapter 8 tells you. So what we could try and do is, just for the heck of it, so what chapter 8 says, come back to your pen, is that we have a mole, and a mole equals 6.022 times 10 to the 23rd things. This is chemistry, so our things are going to be atoms or molecules. Why would we change our definition? Depends on what we're looking at. If we're looking at atoms, we want mole to be equal to atoms. Okay? If we're looking at molecules, we want it to be looking at molecules. Okay, so that's chapter 8. Chapter 9 says from a balanced equation, I can convert the moles of substance A to the moles of substance B. There's chapter 9. Okay, done. Okay. that is it. All you end up doing with the rest of those chapters is some manipulations and multiplications within those. Okay? Chapter 8 does go through a big volume analysis. We're not going to look at volume right now with respect to moles. We'll look at that when we talk about gases. Okay? Because it makes more sense to talk about it there. At this point, what we're going to be concerned about are the number of atoms, okay, which then relates back to moles. And then we'll also look at how we can relate that back to mass. Okay? So the only real new thing is what's going on with this atoms or molecules idea. Okay? So before we really get into that, let's make sure we remember how to do dimensional analysis. How do we solve this problem? Where do we start? I think I heard the end. This equals what? What does our answer need to be? Micrograms. Okay. What are we starting with? We're starting with 325 milligrams. Okay. Just like we did way back when, we then need to do some conversion factor. Why do we need a conversion factor? Does milligrams equal micrograms? No. So we need to do a conversion factor. Ideally, what we would do is set up our new conversion factor, and what we need to do is evaluate what unit changes need to happen. Does milligrams show up in the answer? No. So what do I need to do to that milligram unit? It needs to be gotten rid of. How do we get rid of it? It needs to show up on the bottom. Well, what unit do we want as our final answer? Micrograms. And where does that show up? In the numerator. So ideally, we go through and we figure out this conversion factor. Do we have a conversion factor between micrograms and milligrams? No. So now we're kind of stuck. So what we do is pause and reevaluate. Is there something that I can relate these two to? What is in common between micrograms and milligrams? Grams. So what I'll do is convert my milligrams into grams. Okay? Well, what's that conversion factor?
1 gram is equal to 1,000 milligrams.
Okay? I like where you're going with that, but I don't like that math on it. We talked about some reasons behind it. What did milli stand for? 10 to the negative 3. Okay? Your conversion factor that you guys both came up with is technically correct, but it's putting our numbers in wrong spots, okay, from what we've been talking about in class. Okay? You still will get the right answer, it's just different meanings. Okay? What are our units now? Grams. Our milligram unit cancels out. So cool, we got rid of the milligram issue, but now we have grams. Is grams our final answer? Nope. So we need another conversion factor. Do I want grams to show up in my final answer? No. So denominator. What do I want in the numerator? Micrograms. Do I have a conversion factor between grams and micrograms? Wasn't one I told you to memorize, but 10 to the negative 6 grams is 1 microgram. Okay.
This whole, ever since we did this way back at the beginning of the semester, this whole system has always been so confusing for me.
So the other approach that you can go through and do is do each calculation individually. Okay? Which I'm not going to argue with. That absolutely works. The issue with doing each calculation individually is it's going to take up a lot more space on your paper. And the next issue is that you may not see the relationships that you need to address and cover to get through it. Okay? The idea behind this relationship is stepwise. What do I have? What do I want? How do I get that to occur? Okay? And you've done that 1,000 times before. In your everyday life, you do these types of conversions. But you've internalized them in your head, and you've removed the mathematical symbology and notation from it, which means you lost all comprehension of being able to apply it to a new situation. Okay? So it's really going to come back and haunt you if you don't figure out what's happening within this. Okay? So let's take another stab at this. Okay? And the stab, because you're the one that addressed it, what would you do? What's your first step?
Well, you've basically got 0.325 grams is what you have.
So what you've gone ahead and done was the very first step of our calculation.
Right.
Okay? Which is fine. You did the very first calculation, converting it into 0.325 grams. So now I'm going to write through that conversion factor. To do that, what did you have to do? 325 divided by 1,000, or, I think I heard it, times 10 to the minus 3.
Right.
Okay? When you did it in your head, you kind of removed the unit notation. 10 to the minus 3 what? Well, in our answer, grams showed up in the numerator. It's 10 to the minus 3 grams and 1 milligram. Okay, what do you do next?
So basically, the milligrams is...
Well, we don't have milligrams. We've got grams.
Okay.
What do you do next? Okay. And this pause is why I'm saying you should be addressing what you get your information up there. Okay? We need to get to micrograms. If you write it out, you can see what you're trying to get to. If you start doing your conversions, it's not wrong. Your conversion is absolutely 100% correct. But now what happens? It's, what do I do now? Okay? The idea behind the dimensional analysis setup is that we can see both where we currently are and where we want to go. Okay? And we can do an extra step in here and maybe throw in this microgram. So now you can see where you need to go. Okay? And the issue that you're hitting here is how many times have you used microgram as a unit? Never. Have you used milligram as a unit? Yeah. So what you've done is internalized and know how to do only the thing that you know how to do. And as soon as you're asked to do something else, you're stuck. That's the idea behind formalizing the notation. Okay? You did this calculation. Okay? And instead of internalizing it, write out your calculation. Remember, I've said this now multiple times. Every time we attack a problem, first step, write it down. Get it on paper so that you can start to evaluate. Okay? That next step of the conversion is admittedly difficult. Okay? Either for you going from grams to micrograms, but now you're kind of lost because you have no idea with no background on how to place those individual pieces. If we go back to the dimensional analysis, what we go through and evaluate is say, okay, my milligrams are gone. I need to somehow get to my answer. My answer has what units? Micrograms. And those microgram units are where? In the numerator, which means my conversion factor, so the left side of my equation, had better have micrograms where? In the numerator. Okay? So it's evaluating not I need to get here, it's where do I need to get? What information has to show up? Okay? Based on process of elimination. Not what's my next step, but I need to get here. To do that, I know I have to head that direction. I don't have to get there in one step, but I need to head that way. Okay? We can now go back and see what other information we've got. If we just multiply by micrograms, that's not going to work out for us. We have to evaluate our gram unit. Does grams show up in our answer? Does grams, the unit gram, show up in the answer? No. Microgram does. We got to separate the English away from this. It's a microgram, not a gram. If we take a look at our calculation, what unit is showing up in our calculation? Grams. That gram unit cannot be there. Why can it not be there? It's not in the answer. So it must be removed. How can we remove it? We have to divide by it. Okay? So I may not know what the conversion factor is, but if this is a show your work problem, I've now put down 3/4 of the work and said, the only thing I don't know how to do is this conversion. Please give me some points. Okay? Maybe with other people that doesn't work. But for me, that works. You've proven to me that you know exactly what you need to be setting up and putting into the calculator, and we can talk about the calculator as the next issue. Okay? You've set up a huge section of that work. The next part is the actual interpretation of what the microgram is. That goes all the way back to whatever those earlier chapters were. Okay? And you would have to then have that memorized. And this was the issue that we said with the milligram. You guys both came up with 1,000 milligrams as 1 gram. It's not that that's wrong, but that's not how we told you to memorize it. Which meant you're now trying to interpret what I told you to do with what you think you should do, and they don't overlap. Okay? What does micro mean? 10 to the negative 6. Okay? That 10 to the negative 6 always applied to our base unit of grams. In our conversion, that means we need 1 up top. Now we've got that information. If you just give me 0.325 grams, now I need to do something magical to get micrograms, you've shown no understanding of what's happened. You've internalized all of your calculations. I can't give you any points because all you've done is showed me an instinct. It doesn't matter if that instinct is right. You haven't shown me that you understand the material. So I need to see that understanding. Okay? And that's what this method organizes and puts together. You could put in some extra calculations. This could help to get to that 0.325. But once you write 0.325 to start out with, I've got no understanding of how you got that number. Yeah.
See, I just write out the whole number. Like 10 to the negative 3 is 1,000, or 1,000. So I just write out that whole number. So when I'm done, I can just
10 to the negative 3 is not 1,000. It's 1/1,000th.
It's gonna stop talking.
Okay. So, well, no. You've got the right idea. 10 to the power of 3 is 1,000. What did we say the minus means? You need to run that calculation in the opposite place. Okay? So if we go through and do this, whoops, sorry, well, I needed to erase that anyway. We could say that this is 1,000 to the negative first power. Because you said 10 to the 3 is 1,000. You okay with that?
Yeah.
Okay, so what we did was did 10 to the third times negative 1. 10 to the third gives us 1,000. Okay, so far so good. Everybody have any complaints, or anybody have any complaints about that conversion?
Well, it goes the opposite way. Because it would be 1,000 milligrams.
No. 1,000 to the negative power grams is 1 milligram. What did the negative mean?
I have no idea.
You need to put that number in the opposite location. Where's the number right now?
Wait, so it just means switch it so grams on the denominator?
So the number, not the unit, the number needs to happen in the opposite place. What's the number? 1,000.
Yeah, that's how I set it up.
Okay. So the argument that I'm saying is that you've memorized 1,000 milligrams as 1 gram. What happens when it's when it's a microgram?
Well, I don't know. It's a gram
Okay. Nanogram.
to the 12th, so you just write 12 zeros in.
Okay. And so what's helpful is you had that memorized, which is different from how the textbook presented. It's different how the lecture presented it. Okay. So far everything you've said is absolutely correct. I'm cool with it.
Yeah.
The issue is when you're wrong, and that's what I'm afraid other people are going to have.
Okay.
Okay. So, and I didn't say that you were wrong at any stage. Okay. It's just how you get that number. So everything that you've said is absolutely correct, and so far everything I've asked you've been consistent on. I'm cool with that. Okay. The issue is how you get that number shifted around. Okay? The reason behind formatting this, okay, in this fashion, you may have known the milligram. We already encountered an issue with the microgram. What happens when I move to moles? Have you ever used a mole unit before? Okay, one person.
One of those days.
It's long. How about mole conversions? Okay, now I can say people. Okay, 3 or 4 people. You're running into conversions that you have not seen, which means you have not internalized them. You do not have that instinct. You have to methodically come up with a formalism for your instinct. You have to explain why you're doing those calculations. Otherwise, you're ultimately going to run into issues and not be able to solve the problem. Okay? As far as calculators go, Okay? This is a common issue that I've been seeing a lot of people have with the calculator. With this method, what do we do as far as our calculation? Multiply everything in the top. 325 times 10 to the minus 3, 0.325. Everything in the bottom equals 10 to the negative 6. Now I can punch it into the calculator. What do I punch into the calculator? 0.325 divided by 10 to the negative 6. If you instead decide to do multiplication and divisions at each step, you're going to run into an order of operations issue almost undoubtedly, particularly when we bring in exponents. Okay? So you need to watch out for your orders of operations when it comes to the calculator. Okay? You will get answers wrong. Okay? How many sig figs should we carry in our answer? Everybody's favorite question. Why is it 3? We've got 3 sig figs in our 325. Our conversion factor here. How is it infinite? It's an exact value. The next one, also infinite. We carry 3 sig figs. Will you get tested on sig figs? Probably the final. I'm not going to try to test you on sig figs as far as the exam 3 goes. It might show up as an accidental thing, but almost undoubtedly you should be fine as far as sig figs go. Okay? So now what we're going to do is take this a step further. Let's try another conversion. A farmer has 72 chickens, and each chicken lays 2 eggs per day. How many eggs can the farmer collect per day? What units do we want for our answer? Eggs. What information are we starting with? 72 chickens. Do chickens equal eggs? Not really. So we need to do a conversion. We need to get rid of the chicken unit, and we need the egg unit in our numerator. What is our conversion between eggs and chickens? 2 eggs equals 1 chicken. Interesting point. Definitely heard the answer, 36. Is that right? No. What did you do? You divided. Why did you divide? You guessed, 50-50. Why is it bad to divide? Because if you look at the units on your work, you don't want to divide because then you have 2 eggs. We'd end up with chickens squared over eggs. Well, that doesn't really make any sense. Okay? Or if we left the units the way we were, we'd said 1 chick, or what would we have? We'd have 1 egg is produced by 2 chickens. Okay? Which is also not what the question stated. So the idea is to organize what the sentence is saying and put it into a mathematical notation that allows you to interpret it. Okay? Here's how we're bringing up moles. Any ideas how we're bringing up moles with this example? How many eggs do we get as an answer? 144. Interesting thing about our farmer. Can't deal with numbers any bigger than 100. Once he hits 100, freaks out, mind blown, can't deal with it. How can you still tell him how many eggs he's got? Okay. What you can go through and do is teach him that, hey, I'm going to pile all of these eggs together. Here's a new unit. What's that new unit? We're going to say eggs is going to be related to my new unit, and my new unit happens to be a dozen. How many eggs make up my dozen? 12 eggs equals 1 dozen. So you can explain to him that here's a dozen, or here's a group of eggs, and I'm going to say this equals a dozen. Okay? So now he understands what that grouping is, and now you go through and say that your answer is, instead of being eggs, it is a dozen eggs, and our answer becomes 12. Now I don't have this massive big number that I can't possibly comprehend. I now just have 12. I can understand and manipulate and deal with that. Okay? It only requires 2 toes. Yes?
How do you count that 12 egg equals a dozen?
Okay? So this might be a language barrier maybe. A dozen is defined as 12 of something. Okay? So that's something that we grow up with. When you go into the store and you buy eggs, how many eggs do you buy at any given instant? You usually buy them in sets of 12. That 12, instead of saying, oh, I'm going to the store to buy 12 eggs, you say, I'm going to the store to buy a dozen eggs. Okay? So it's just an extra unit that we created, now that I think about it, quite possibly because our farmer couldn't deal with numbers that big. Okay? I'm not trying to make fun of farmers, I'm just saying. Okay? So the unit that we're creating there is so that we can shrink down our final answer into something that makes sense to us, that we can kind of wrap our heads around. Okay? Why was this important for chemistry? Well, we invented a new unit too. Instead of being a dozen and 12 eggs, we went through and said our new unit is a mole, and that mole is not 12, it is 6.022 times 10 to the 23rd atoms or molecules or whatever we want.
So
Okay.
just whatever you're talking about?
So ultimately, whatever you're talking about. Yep. And the important thing to remember here is that this is not a measurement. This is a count. This is a number of things. Okay? When we look at grams, what does grams do? It's a measurement. It's a measured value, not a count. Okay? We won't look at mole equaling grams because grams is a mass, moles is a count. We could count out the number of things that weighed a gram, but that's a pretty useless conversion for us. Okay? So it's always a count of these atoms. So our mole is a really, 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 really big dozen. Okay? So that is chapter 8. Introducing that new unit, and ultimately that conversion factor is really what we're driving around. And I'm going to make the argument that that conversion factor you have already seen in a little bit later. Okay? Chapter 9. Okay, so we're going to skip through chapter 8 now. All that's the same stuff. Chapter 9 goes through and says, okay, we're going to look at equations now. So in this equation, I want to know how we make that bicycle. What do we need to make that bicycle? Hopefully you guys are very limited in your parts knowledge. Oh, okay, you already said more than I wanted. We need wheel. Let's avoid the chain too. I don't want to draw that.
Frame?
And our frame. There we go. I mean, wheels and a frame. Could we build a bike yet?
No.
No, why not? There's a handlebar. There's your chain. Okay? Can we build a bike yet?
No, we're missing a part.
If we go through and look, we only have one tire. We put one tire on that bike. Great. We now have the ability to wheel it. You tried biking on a one-tired bike? Okay. Unicycle is not a bicycle. To be a bicycle, what do we need?
2 tires.
We need 2 tires. There's our tire with some spokes. Okay.
Need pedals too.
What we've now got built.
You know the quick little motors on them now, they're pretty kind of cool.
Yeah. I hate dealing with those guys. They're so loud. Okay, next issue is what we've built is a balanced equation to make this bicycle. We need 2 tires and a frame. What happens if I only give you a frame? How many bikes can you make? None. How about if I give you 2 tires and a frame?
Sure.
You can make a bike. Or by frame that's drawn on there. Which actually didn't look too bad. All right? We can make our bike. What happens if I give you 4 tires and 1 frame? But I gave you 4 tires. Why can't you build me 2 bikes? I only got 1 frame. Okay? The information that we are taking advantage of is the coefficients in front of each of these objects or each of these things within our equation. Have we seen these coefficients before? Absolutely. Look at a balanced equation. What is the balanced equation doing? We take part A and part B and we put them together to make part AB. Okay, in a combination reaction. So each of those reactions we've looked at evaluate what parts are coming together to make our overall thing at the end. Okay? other issue that shows up within this, okay, I said 4 tires in one frame. And you said I could only do one bike. Okay, why? I would need 2 frames to make 2 bikes. So with only 1 frame, that is now my limiting factor. I can't make any more bikes until I get another frame. So what we've generated here is a limiting reactant. What would our tires be? Okay, if I gave you 4 tires, whoa, that should be a 1. We only get 1 bike. Our frame ends up being our limiting reactant. What happens with our tires? 2 left over. So what do we have? We have a reagent in excess. How do you know it was 2? You did the subtraction. You said 2 go into the bike, 2 were left over. Okay? It may seem relatively simple here, but then when we take it away from it being something that you can physically see and turn it into, say, something from our periodic table, now it becomes ridiculously difficult. Why does it become more difficult? How many of you can see a reaction? See the atoms physically changing places? You can't. That is physically impossible for us to see. So when we're looking at a chemistry equation, what we're trying to do is draw out, bring some meaning to something that we cannot physically see, and try and draw predictions about what things can happen with that. How many products can I make? How many products should I be adding? Do I have something that's limiting my reaction? Do I have a whole bunch of extra stuff? If I got a bunch of extra stuff, I shouldn't put it in there. Because once I put it in there, now it's contaminated, and I can't use it again. Okay? So what we're trying to do is take advantage of the information found within a balanced equation and try and manipulate that to our advantage and do some conversions and calculations with that. Okay? So let's go through and start actually punching some numbers. So let's take a look at an equation. Okay, an equation and a question. How many molecules of CO2 are necessary to make 2 molecules of sodium hydrogen carbonate? Any guesses? 6. That's an interesting number. How'd you get 6?
Because there's 3 on the reaction side, and then that only made 1.
There's 3 what on the reactant side?
CO2s. Oh, just kidding, never mind.
Okay, so I'm hearing some other people following up with that. We see 1 CO2 on the reactant side, and we see 1 sodium hydrogen carbonate on the product side. So we might say 1 and 1. Problem with that? What's that? Why is it 2 and 1? Our equation's not balanced. Remember, when we looked at our bicycle relationship, we said we needed tires, a frame, and we made our bike. Okay? If we only specified 1 tire, we don't make the bike. Our equation wasn't balanced. What did we have to do? We had to bring that coefficient of 2 in to specify how many of that part we need. So we need to start with a balanced equation. Is our equation balanced? No. What do we need to add to it? 2 here? Okay. So how many molecules of CO2 are necessary to make 2 molecules?
Just 1.
We only need 1. How do you know 1?
It's balanced, right?
You look at the number in front of the CO2. What's that number?
1.
Okay. Whenever I've circled empty spaces, we've almost always said 0. Why is it 1 in this case?
Because when you circle it, it looks like a 0, so you read it.
Yeah, I know. That's why I did it. Why is it 1? If we write the formula, there had better be at least 1 there. So all we're doing is being lazy and not specifying that 1. Okay? So there is absolutely a 1 there because we wrote that formula. So it requires 1 molecule of CO2. Okay? Cool. I want to now go through and do this in the lab. So I'm going to measure out 1 molecule. Can I measure 1 molecule? Can I count 1 molecule? Can I see a molecule? No. Okay, so how do I make measurements in the lab? What? Moles is just a number. So it's a really big number. Can I count 60,000 atoms?
I thought moles were a count though.
They are a number, a count of an individual type of atom. So you're right. Okay? Mole is better, but doesn't help us. Can I count 60,000 atoms? Now I'd say it's probably even worse than that because I probably can't count that consistently well, and I still can't see them to count them. We could look at mass. Okay, when we move into the lab and we tell you to get something, get a certain chemical, what do we tell you? Get the mass of that. Okay? So instead of looking at the number of molecules, let's go through and look at the mass. What's the mass of 2 molecules of CO2? Particularly in AMUs, how we've been looking at this. Yeah, tell me through it. Why'd you say 12? Looking at the periodic table to tell you that a carbon atom weighs 12 AMUs, which is a mass unit per atom of carbon. Okay? What would we want to add that to? The mass of our oxygen, AMU. What do we get as an answer there? What do you mean? There we go. That's what I wanted to hear. Why do we have to multiply by 2? There's 2 oxygens. What's our mass come out to be? 44 atomic mass units, which is the mass per now 1 CO2 molecule. Molec per molecule. Okay? How do we now figure out the mass of 2 molecules? Painfully long and slow? Write it out. Dimensional analysis. What do we want? Our answer needs to be AMUs. What are we starting with? 2 molecules. Our conversion factor. We need to get rid of molecules, so we'll put it in the denominator because it shows up in our numerator already. And we want AMUs. Do we have a conversion factor between AMUs and molecules? 44 AMUs equaled 1 molecule. What did we do? We multiplied by 2. Absolutely right. Set up the format. Get the equation formatting down. Get that notation down. Okay? That way you can't make the mistake of accidentally dividing when you should have multiplied. Okay? And we go through and we get what? 88 AMUs. Cool. Take a look at your balance. What units does your balance spit out? Grams. So is our AMU mass going to be helpful? No. Okay, well, can we convert AMUs to mass? Yeah, okay. Or to grams, sorry. So instead of doing AMUs, let's now get it into grams. Okay? So we could go all the way back to the beginning and do our conversion with our AMUs and all that fun stuff. Or what we can do is say that we can now pick up at 88 AMUs. 88 AMUs of CO2 needs to now be converted into what? Grams of CO2. Okay? Take a look at our conversion factor. What does our conversion factor need to have in it? Grams, which needs to show up where? Y in the numerator. That's where we want it at the end of our reaction, or at the end of our calculation. What else needs to show up? Where do the AMUs need to show up? In the denominator. Is there a conversion factor between grams and AMUs? Oh, shucks. It's on the very next click, but then it deletes all my stuff. 1.661 10 to the negative 24th grams equals 1 AMU. Yep, we want the full deal. 661 times 10 to the negative 24th grams equals 1 AMU. Why did I put the 1.661 times 10 to the negative 24th with the grams and not the AMUs? Because when you look at the conversion factor that I'll put up here in just a second, that number shows up in front of the gram. It's with the gram unit. Okay, so it always stays with it. Okay? Now we could punch this into our calculator and we could get a gram value. Does everybody have the number written down and perhaps a calculator to give me a number on this? Okay. Based on your laughing, I'm going to guess you've got a number that's really, really small. Okay? So there's our conversion factor. What was the number? Oh, sorry.
1.46.
Whoops. Sorry. 1.46.
168.
10 to the negative 22 grams of CO2. I think I can agree with that. Hopefully everybody else gets the same number, or at least close to it. Okay, cool. What does our balance measure out to? Balance goes 0.001, also known as 10 to the negative 3 grams. That's ballpark, right? Our balance could approximate 10 to the negative 22. We're missing 19 zeros in our accuracy. Is our balance going to be able to measure the mass of 2 molecules of CO2? Not even close. Okay? This is where we run into a massive issue when it comes to chemistry. We want to be able to react things with each other. We have an understanding of how they react, the individual components as they come together. But if I want to measure out a molecule, I can't get the weight. I do not have the physical ability to do that measurement. Okay? So what does that do to chemistry as a field? Kills it. We got nowhere to go from there. Until some very smart person came along and said, you know what? I don't want to measure out 2 molecules. I'm going to measure out a number that is big enough that when I go to put it on the balance, I don't get this negative 22 number. I get, hopefully, nothing there. Okay, so instead of measuring out 2 molecules, I'm going to measure out 10 to the 22nd molecules. Now when I go through and do the calculation, instead of ending up with 1.46 times 10 to the negative 22 grams, I'm going to have 1.46 grams. Okay? Now I've got something that I can actually measure and I can do something with in the lab. Okay? So that's kind of the intent behind the mole rule. Okay? We can't measure that mass, so we invented a new unit to allow us to measure that mass more appropriately without having to deal with these ridiculous exponential values. Okay? That that conversion that we came up with was discovered or named for Avogadro. 1 mole is equal to 6.02 times 10 to the 23rd atoms, or molecules. This allows us to get into that measurable scale. Okay? As much as we would like to say this is a brand new number and entirely awesome all on its own, I would argue that we have already used this number. When we did our conversion from AMUs to grams, what did we do? Said 1 AMU was equal to 1.661 times 10 to the negative 24th grams, right? And when we put it into our calculation, we could put it in any number of ways. We could have gone AMU over our 1.66 times 10 to the negative 24th grams. Could have gone the other way, depending on what we were trying to solve for. 24th grams over AMU. Why address this issue? Okay, well, what's 1.66 times 10 to the 24th divided by 1? Yeah, same number. Okay? What is 1 divided by 1.66 times 10 to the negative 24th? I would argue it is a very large number, but I want some details. Someone give me that number.
1.66 times
10 to the negative 24th. 1 divided by 1.66 times 10 to the negative 24th. What does that equal?
6.0240969.
Okay. I'm going to argue that you have a calculator mistake, and you should talk to me after class to make sure you don't make that calculator mistake. Huh. What's that number? That's our mole number. The conversion between moles and atoms is the exact same conversion as between going AMUs and grams. All we've done is shifted where we've decided to put that number. We have done this calculation already. We just used Avogadro's number to go through and do the calculation. Okay? So that is kind of neat. We've already been using this number to do our calculations. We just looked at the wrong scale, so it didn't quite become as obvious to us. Okay? So what we want to go through and do is now use this number to get us to a point where we can actually measure quantities. Okay? So let's take a look at a couple options here. So if we take a look at 3.42 times 10 to the 21st atoms of aluminum, how many moles of aluminum are there? So, how do we set it up? Step 1 equals moles of aluminum. I think I heard that float out there. Why is the aluminum important? We need to make sure that we're talking about aluminum. In this equation, how many different elements are we talking about? 1. So how important is it here? Not really. We're going to talk about moles or grams or atoms. It's always going to be aluminum because there's only one atom there. What if I move to a reaction equation? How many different atoms do we deal with in an equation? We get several of them. Now it becomes critically important to make sure that our unit is complete. Not just our mass or our moles, but what is the mass in moles of? Okay? So our units are now not just a single unit, but 2 pieces. You must include both pieces when you go through and solve these problems. If you drop off that second piece, you run the likelihood of making a mistake further on down the road. So watch out for that. Okay? What did we start with? I hate these problems. These numbers are big. 3.42 times 10 to the 21st atoms of aluminum. Okay? Look at our conversion. What do we want to get rid of? Atoms of aluminum. What do we want in our answer? Moles of aluminum. Do we have a relation? Sorry, go ahead. We could now cross out the atoms. I want to get numbers in before we start crossing out units, but you've got the right idea. So that's exactly why we set it up in this format. Our atoms of aluminum can cancel, and we end up with moles of aluminum. What's the relationship between the moles of an atom, or the moles of an element, to the atoms of an element? Avogadro's number, 1 mole, is 6.022 times 10 to the 23rd atoms. What happens? Now when we go through and calculate, we end up with...
Are you going to want us to use 6.022 or 6.02?
We'll address that in just a second. Good question, though. Don't let me forget that. 0.0... I don't remember what the number was. 681? 5681? 681. Give me a number. What'd you say?
Hold on.
Who's got that first?
Not me.
Did you know right?
You didn't multiply it by the 3.42.
Oh, that was it.
Can someone give me a number with some more sig figs here?
5.791736353.
No.
No.
Okay, I like that number a little bit better because that sounds kind of familiar. 5, 6, 7, 9, 2.
Did I do this wrong?
All right. How many sig figs need to show up in our answer? Three sig figs. 3 or 4, depending on what you use. Our answer needs to be 3 sig figs. 1, 2, 3. First insignificant, what's its relationship to 5? Bigger, so 8. And now we have our answer. Sean had a good question about what number should we use for Avogadro's number, 6.022 or 6.02? Okay? Really is going to depend on the number of sig figs you want in your answer. Nothing you're going to get is going to have more than 4 sig figs, so 6.02 is going to be perfectly all right. You can stick with 3 sig figs. If you want to carry that extra decimal, sure, go ahead. The only reason why it's carried up there is for some reason when I memorize the number, I've memorized that extra 2. Okay? I guess it's more rhythmic in my head, so it's stuck. Okay? I will give you that on the test. That said, how important is this number to all these calculations? Really important. You'll be using it again and again and again, and probably still again and again. Which means, yes, even though it's given to you, if you have to keep flipping back to figure out what the number is, you're wasting time. It makes sense to go ahead and memorize this.
Wouldn't it be, like, I don't know, would it be unlimited sig figs? Isn't that an exact?
3.42, we don't have, we've got 21 decimal places after that that we know nothing about.
No, I'm talking about the moles to atoms. Would that be infinity?
The moles to atoms there is still technically the same issue. Avogadro's number does carry out. You can look up, they've got it to 15, 16 places, I think, now. Okay. Is it ever going to be a decimal value?
I don't know, possibly.
What does a decimal mean?
It's going to be small.
We have a fraction of whatever we're looking at. Can we have a fraction of a single atom? No. We'll never have a decimal value for Avogadro's number. Okay. Even though we see 6.02, remember that 10 to the 23rd is carrying out a lot of places to make sure we're looking at an exact number. Okay? Questions on that? Try another one. This one's a little bit trickier. Okay, I want to let you guys go ahead and give this a try. If you've got a question, raise your hand. I'll come to you. In general, this is set up. 2.40. We know our answer needs to be atoms of oxygen. Our formula for an oxygen atom is? Formula for an oxygen atom. O. What is O2? That is our formula for the diatomic element of oxygen. This asks for the atom of oxygen. Our formula is O. Is that important? Yeah, that's going to be really, really important. When we go back and look at our problem, we start with 0.240 moles of O2. So we could go through and do our conversion. We want to get rid of the moles unit, and we want atoms to show up. Okay? Atoms works when we're talking about an atom. Is O2 an atom? It's a diatomic what? Not atom. It's a diatomic molecule.
So it's a molecule.
So it changes our unit ever so slightly. Does that matter too much? Kind of, sort of. It depends on how careful you are with your units. What happens? Our moles cancel, and we now have molecules of O2. Okay, cool. What was our answer supposed to be? Atoms of O. Are we at our answer? No. We're missing a conversion factor. What is that conversion factor? I need to be able to convert molecules of O2 to atoms of oxygen. Well, crap, I don't know that. Yeah, I do? How do I know it?
Well, I said before, you can swap mole as either atom or molecule.
That's what we did right here. Even if we make that atoms, it's still atoms of O2, not atoms of O.
The molecule is made up of 2 atoms. You know it's 2
Yeah.
atoms because of the subscript.
Take a look at your formula of O2. What does that formula mean? There are 2 atoms of oxygen in your compound, or in that molecule. So we now can go back and say there are 2 atoms in 1 molecule of O2. Now when I go through and do the math, I end up with my correct answer. Okay? So make sure that you answer the question asked. If it's asking for oxygen atoms, That's very specific, saying we're looking at an atom. The question gave you information as O2. Okay? Not only do we have information stored as an amount in our balanced equation, but remember, before we could even balance an equation, what did we have to do? You have to balance the formulas. Why do we balance the formulas? That gives us the amount of the individual atoms that went into those compounds. If we don't have those amounts right, we can't balance the equation properly. Okay? So we get two big sources of information, both in our formula and in our equation. Okay? Hugely important. Okay? Again, all we're trying to do is organize via dimensional analysis, set up where we're trying to get, where we're at, and make them match as best we can. Just like we did with balancing, for that matter. When we looked at an equation, we know what we want to get to and we know what we started with. So what did we do? We had to adjust the numbers until we had the same number of atoms on both sides. Otherwise, we created or destroyed matter and the whole problem fell apart. Mathematics is following a very similar idea. We're just tracking it with units. Yes?
Well,
Sorry, I talked a whole lot.
It's okay.
What's the answer?
Yeah, that's what I was thinking.
Okay, we're looking at 10 to the 24th is going to be probably your mistake. You should be getting something on the order of 10 to the 24th, positive.
Why
I just don't understand why you multiply by 2 atoms.
See, that's what.
It's kind of like the chicken egg example. So you have 144 eggs.
Okay, so let's break it down.
You know?
So, numerator. What do we do with everything in the numerator? Multiply it out. Okay, I don't have a calculator, so I'm guessing at some of these numbers. 0.24 times 6.02 gives you
1.445
times 10 to the 23rd. Yep, times 2. Next calculation, and then we'll divide that all by 1. Why divide by 1? Look at everything in the denominator. Everything is 1. So 1.445 times 2. Oh, I did do that math wrong. Sorry, it is 23rd. Okay, what was the number? 2.890 times 10. 10 to the 23rd. Okay, and our units are atoms of oxygen. Is this a correct answer? We have to address our sig figs technically. How many sig figs should we have in our answer? 3, which means drop our 1 and we're all good. Okay? Did it come out the same? Did you do it right? Good. Okay. Sorry, that's what I get for trying to guess at what's happening with our exponents. Okay? Questions? Okay. Almost a new question. 1 mole of several substances. So your textbook has this picture, and it shows a whole bunch of different substances floating around, and you'll notice that it looks like we get differing amounts of each of those substances. That's kind of odd. It's the same number of that molecule. Why do we get different amounts? Our masses and ultimately the volumes of each of those atoms are also different. So when we look at solids, we're going to see differing amounts of each of those species as far as moles go. Okay? Because each of those solids, when we look at the solid, each of those atoms must be interacting with each other. Okay? What happens when we move to a gas? This is kind of a foreshadowing for after the exam. When we move to a gas, we make a couple assumptions. Okay? We make these assumptions because it makes our life easier. Number one, we assume that the atom is so small that it does not take up volume. Does that make sense? Physical sense? Okay? Remember, we're looking at an atom being super, super tiny. So if I take a grain of sand and say that's my atom, and we look at the volume of this space, does that grain of sand really detract from the volume of this room? No. Not really. So we assume our atoms do not take up volume. One of the next big things that we assume is that the interactions between them is relatively non-existent. we don't see our atoms interact with each other very much. Why? That's what happens when we move to a gas. Everything breaks apart and they're free flowing, right? Okay. What is that going to do with our volume? So it doesn't matter what my atom is, it does not see any other atom, and it has no volume. If I take a mole of any species, what would I predict the volume to be? Tricky. It's the same. Okay, which was one of the things that shows up in chapter 8, which is not on the test. We end up with something known as a molar volume. The volume of any gas is the same as long as we look at the same number of particles within it. Kind of neat. Okay? So why do we go through and use Avogadro's number? So this is the next big kind of section here. We could look at the mass of 1 mole of protons. I think that one's kind of a boring example, so let's switch it up. Let's look at the mass of 1 mole of carbon atoms. Okay? And I want mass in grams. Okay? So, dimensional analysis. Everybody's favorite. What are we aiming for? Grams of carbon atoms. What are we starting with? 1 mole of carbon atoms. Okay? Set it up again. Moles need to disappear, and we need grams to show up. Have we discussed a conversion between gram and moles? We haven't talked about one yet. Okay? That's going to be the conclusion of this slide, is that we do generate one. Okay? We don't have that relationship. The only place that we've got right now to get mass is from our periodic table. And the number on our periodic table was what? The AMU, the atomic mass unit, right? So that's the mass per atom. Well, I can get mass, but I have to know how many atoms I've got. Can I convert my moles to atoms? Yeah. Avogadro's number, right? 6.022 times 10 to the 23rd. Atoms is 1 mole. So cool, now I'm into an atom unit. Digging it. That's helpful. Okay. What's the mass of my atom for a carbon? Okay. So I'm trying to convert my atoms into AMUs. And I know my AMUs is 12 AMUs per 1 atom of carbon. How do I know that? Periodic table. But I wanted the mass in grams, gosh darn it. Yeah, that was fun. How do I get AMUs into grams? That conversion, I like it. We have 1.66 times 10 to the negative 24th grams was 1 AMU. That is the conversion factor between grams and AMUs. That is something that I will tell you on the exam. It will be given to you. Okay? I make the very strong argument that you don't need that. Okay? Punch this into your calculator. A lot of different little things to punch in here. This one I actually know the answer on. Big reveal. Dun 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 dun. Da 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 da. Yes. Yes and no. You'll really only need 3 sig figs for everything. It's not a bad idea to carry out these out to the 4th significant digit. You'll notice that I always drop it. It's organic chemist laziness. The answer was 12. You should all be getting out 12. How was I able to do that mathematically in my head so wicked fast? 6.022 times 10 to the 23rd is the opposite of 1.66 times 10 to the minus 24. Remember, we showed that just a few slides ago. Those two cancel each other out. So when I go through and do the math, this is 1 times 12. Yes, that's one I can do in my head, thankfully. Okay? What does that mean? Where did 12 show up? Periodic table. The number we pulled off the periodic table was our AMU. Guess what else it is? It's the molar mass. It is the grams of that element per mole of that element. That is huge.
What'd you say?
Right? What I said was the atomic mass on the periodic table is used as our molar mass. What are the units on mass? Grams. Molar, we're looking at molar affecting our grams. It's the grams per mole of that substance. So if I want to know how many grams are in a mole of iridium, what do? Periodic table, and I say what number? Good question. That's fair game. IR. 192.22 is the grams per mole for iridium. What's the molar mass for calcium? 40.08 grams per mole. Why is this so ridiculously important? I now have the ability to convert grams into moles. Why is that important? What did moles measure? The number of something. I can now convert the number of that species into a mass. Why is that neat? When I walk into use my balanced equation, what does that equation give me? The number of those species. When I walk into lab, what do I need to measure? The mass. I now have a conversion factor to allow me to go from my lecture to my lab. Okay? And vice versa if we really wanted to. Okay? Ridiculously important. Yes?
We got this question on the test. We just write for the work, look at the wall.
I would never ask this question for work. Yeah.
Choice.
Multiple choice is a possibility, yes. Okay? So what we're looking at from these chapters are ultimately a list of conversion factors. You'll notice there's no numbers on these. And that's really only because 2 of these can give you numbers. Avogadro's number, sure, we can come up with a number there, 6.022 times 10 to the 23rd atoms per mole. And we could also do the grams to AMUs as our cheaty method, our 1.66 times 10 to the negative 24th grams equaling 1 AMU. Both of those numbers will be given to you on the test. The one that you should probably commit to memory would be Avogadro's number. Okay? Not only because you will use it super frequently, but talk to any chemist and what do they get all giddy and excited about? Freaking moles. Okay? I still don't quite understand it. Apparently I'm not a good enough chemist. Okay? I just don't understand the fascination with moles. Okay? It is a useful tool, but ultimately all it's doing is getting us to the fact that our periodic table gives us grams per mole. Okay, that's nice. I accept that. That's neat. That's valid. I don't need to glorify the fuzzy little animal. Okay? So it makes our mathematics easier, but do we have to use the number? No. Why not? Because we don't deal with atoms. We deal with moles. We look at a larger amount. Okay? So what about the molar mass? Why do I not give you a number for grams to mole? It's different for every element, different for every compound. You have to calculate it. If I asked you for the molar mass for CO2, what do? Periodic table to do what? You add up the molar mass, or your molar mass for carbon and your 2 oxygens. Okay, and we end up with, what do we decide? 44 grams per 1 mole. Okay. Chapter 9 gives us our balanced equation, converting molecules into molecules or moles into moles. Again, hugely important as far as those calculations go. Okay. This is all on the exam. Okay. Ultimately, all this is 2 new conversion factors, and you're doing the exact same conversion factors that you did at the very beginning of the semester. So most of this is review. Yeah, it looks crazy new, and I'll accept that, but most of it is review. Okay? We do have a whole bunch more problems that we could go through and look at. We just talked about how we could get our molar mass by calculating that out. What if I wanted to manipulate the molar mass? How do I get the mass in grams of 0.532 moles of copper nitrate? Just as we do everything else. Come on, pen. This equals, yeah? Close. Grams of our copper nitrite. Trite. Ooh, fun one. What is this question also testing as I quickly erase that so you can't see it? Test your nomenclature to know that you know that copper nitrite is NO2. You need to be able to come up with that formula. Why is that formula important? Because to be able to convert between grams and moles, what do we need? The molar mass. To get the molar mass, what do we need to know? The atoms that went into it. If we don't know the atoms to look up on our periodic table, we can't solve it. Okay? What do we start with? Our mole, what was it, moles? Yeah. 0.532 moles of our copper nitrite. Do we have a conversion factor between moles and grams? That's our molar mass. We'd look it up for copper. We're at 63.55. For some reason, I'm using more sig figs this time. 14.01. Now the morning will yell at me if they watch this video. I just wrote 14 for them. Oxygen, 16.00 times 4. I take that number. That is now the grams per 1 mole. My number goes up here. Run the calculation. Units cancel. I now have grams. Yeah.
What's that too? Outside that parentheses,
The 14. Why do I have 4 outside the 16? That looks like a subscript.
Because copper has a two, and I'm working through this as I'm saying.
Doesn't have to do with copper.
Like both, like 2 of them, 4
So why is there a 4 in front of the 16 or after the 16?
Yeah.
Look at your formula. There's 2 nitrogens, 2 forward, 2 forward. Okay, we got to take into account our parentheses. So almost all of the other questions are just variations of dealing with these units. I got no problems working through more of these right after class or even in office hours. Okay, that's what the rest of these are. The last thing that I want to draw your attention to, come on. Where'd it go? There we go. Our limiting reactant concept. You will get asked questions on the limiting reactant concept. You will not be asked for calculations of the limiting reactant. Okay? We talked about this already. We looked at the bike example. The textbook, at least the textbook slides, look at making cheese sandwiches. I don't know why they think that's cooler, because bikes are the coolest, right? All we're trying to do is look at the balanced equation and evaluate what do we have more of, what do we have less of, and define one species as the limiting reactant or not. Okay? The limiting reactant is going to be the one that you run out of first. Okay? The one you have extras of would be your reagent in excess. Okay? Is typically the word that's phrased for it. Most people look at the limiting reactant. Why do we care about looking at the limiting reactant? When we look at a reaction, what are we concerned about producing? Our product. What's going to determine our product? The reagent in excess or the limiting reactant? The limiting reactant is always important. Okay? Study guide posted. I'll get